Hello again, physics friends. In this video, we are going to take a deep dive into light and specifically talk about photons and how we know that photons exist. In other words, what direct evidence do we have for photons? And I think that most of this story will be rather surprising and or new to people. If you survey physicists, most of the time you will hear from them that the photoelectric effect, which we'll describe in a little bit, is the direct evidence for photons. In the photoelectric effect, light is incident on, say, a metal, and one electron is kicked out for every photon of light that comes in. At least that's how Einstein described it. And in fact, in 1905, he won the Nobel Prize for this theory. Well, I should say in 1905 he came up with this theory, and then he won the Nobel Prize for it in 1922. Rather surprising as a historical aside that Einstein did not win a Nobel Prize for special relativity, general relativity, or any other of his wonderful contributions to physics, but it was rather his contribution to the world of quantum mechanics and understanding of the nature of light. In hindsight, as we'll see today, that analysis was not quite correct. Although at the end of the day, photons we now know do exist, but using the description of the photoelectric effect to explain the existence of photons is not a complete story, because there are other ways to explain those experimental results without invoking a photon at all. So here we're going to be talking about particles and waves, right? And we might think of an electron as a particle, right? Although we know that the electron also has wave-like behavior. Light, on the other hand, is kind of naturally understood and thought of as a wave, in the sense that the Young two-slit experiment showed clear wave-like behavior with interference and so on. Okay. Now we know that in 1924, Louis de Broglie suggested that particles were also waves. So we also have matter waves. And we now know that light can also behave like a particle in the form of a photon. And our task today is to understand this kind of quadrant of this 2x2 grid here, where objects like electrons are both particle and wave-like, objects like light are both wave-like and particle-like. We want to understand the true evidence for photons as particles of light. One immediate challenge that the wave-like nature of light poses is if you think about exposing photographic film to light. Right? If you treat light like a wave, then you might imagine, just like an ocean wave, that light wave would kind of simultaneously hit the whole photographic film and make a line of light or a sheet of light, in much the same way that an ocean wave simultaneously hits multiple grains of sand on the beach. But in fact, when light hits a photographic film, one silver grain is converted or blackened, and that makes the change to the film. So rather than having a kind of a large extent of the film be affected by the light, only a single point-like region of your film is affected. And these days we don't use photographic film so much, but this kind of behavior is true in all of our photodetectors. So photomultiplier tubes, light comes in and kicks out an electron at a single location at a single instant of time. A CCD camera or a CMOS camera, much like what's in your cell phones, each pixel lights up one at a time and with one photon at a time. So it does seem like when we are detecting light is very much particle-like or discrete. And we can talk, and we will talk of detection of light as a clicking phenomenon. Okay, so when you put a photon detector in the path of light, that photon detector will click every time a photon arrives. Now, I shouldn't really be using the term photon because here we're trying to understand whether light is particle-like or wave-like, so to speak. But it is an observable fact, right, that you get discrete signals, discrete in time, kind of clustering, when you detect light. So somehow this kind of originally diffuse light acts as if it were point-like when you detect it. It arrives at a single place in a single moment of time. And this suggests or argues for a particle picture of light. And yet we want to make sure that we're not mixing up the detection event as being discrete with the actual light as being discrete. And here's an example of that distinction. If you look out the window on a fall day, you might see leaves falling to the ground after a gust of wind. And each single leaf falls one by one. So these are discrete detections of wind. But is the wind really a discrete hail of bullets that picks off the leaves the way a bullet might pick off a tin can? Or is the wind really continuous, like an undulating fluid that rocks the leaves until the stems snap? And I'm quoting here from a textbook on quantum mechanics, actually, called The Quantum Challenge, which is a really beautiful book by Greenstein and Zhejiang that talks about a lot of the modern challenges in understanding and interpreting quantum mechanics. And I really like this way of thinking about the distinction between how you detect something and the true nature of that something, right? So light could be this kind of continuous undulating wave, and yet when we detect it, we see discrete point-like events. And so when we think about detecting light, in other words, when light falls onto a metal or creates a shower of electrons, we have a set of discrete of detection events, these electrons that get kicked out of the metal, right? But does that really tell us that light came in one by one in these particle-like packets? Or have the electrons all been rocked back and forth by a wave of light until they are kicked out of the metal, much as the leaves were kicked out of the tree by an undulating wind? Well, this topic is, there's a wealth of information on it, but I'm going to focus on two specific ways of thinking about this. We'll start with the experimental evidence and then talk about two different ways of interpreting this evidence. So first of all, the apparatus. Here we have a little vacuum chamber where there's no air inside, and light is projected or shined onto a metal plate here. In doing so, what we find is that current starts to flow in this circuit. In the absence of light, there's no current flow. And as you turn the light on, you get current flow. Now, current flows because of the production of electrons, and those electrons must be bridging the gap from this electrode to this electrode, because if there was no electrons flowing here, then no current would be able to flow. There's just a gap, a physical space between these pieces of metal. Okay. So the first thing is that, you can get current to flow if you shine light on this metal plate. And there's two properties of the current that flows. And so there's more specific measurements that you can make with this apparatus, but here are two. So just to talk about something concretely. One plot is the amount of photocurrent versus the intensity of light. Okay, so if you double the amount of light you shine onto the plate here, you double the amount of current that flows in the circuit. So the current is proportional to the intensity of light. Okay. The other observable is that current will not flow, okay, until you have light that has a specific frequency or higher. So in other words, you might not get any current to flow with red light, but with blue or ultraviolet light, you'll get current to flow. So red light has a low frequency, so down here, no current is flowing, and it's not until your light has a frequency above a certain threshold that you get light to flow, that you get current to flow. And here, this graph is showing a linear increase in the energy of the electrons as a function of the frequency of light. Okay, so the higher and higher frequency, the more energy each electron has. Okay, so two things are happening then. Clearly, electrons are being kicked out of this plate, and the energy that they have after leaving the plate is grows with the frequency of light. And if the light frequency is below a certain threshold, you don't get any current to flow. And if there is current flowing and you double the amount of light, you also double the amount of current. Okay, so the first interpretation of this that we'll talk about is that of Einstein. His interpretation was this is direct evidence for photons. And the way he thought about it, and this was in 1905, and as I mentioned before, he won the Nobel Prize for this in 1922. He thought of this in the following way. You have some metal, okay, and inside the metal are electrons, and these electrons can move around in the metal, but they cannot leave the surface of the metal, okay, because they're held on by their attraction to the other nuclei that are in the metal. But if you shine light onto this metal, and light is composed of photons, discrete particles of light, if you will, then one photon could come in and interact with one electron, and the energy that the photon brought in could be given to the electron to kick the electron out or eject the electron. Okay, and two things are going to happen here. You can explain both of these phenomenon using this model. The other piece of information we need is that the electrons are held in to the metal by some amount of energy. We could call it, or he called it the work function. But it's a certain amount of energy that you have to overcome in order to kick out the electron. So he used the symbol phi. Okay, so that's one model parameter here. And then the other is that a photon, which is a discrete particle of light, has an energy that he called E, which is equal to the constant h, which is Planck's constant, times the frequency of the photon. And we can very quickly see that this model accounts for the data very nicely, in fact. We can see that you're not going to get any current to flow until the energy of the incoming light is larger than the binding energy of the electron, because you can't kick the electron out unless you put enough energy in to do so. And so right away we can see that we need a frequency that's bigger than phi over f in order to kick off the electron. So for low frequencies, no electrons are kicked out, no current is flowing in the circuit. But then once you exceed this threshold, you will get current flowing. And second of all, the energy of the electron is given by the leftover energy after you kick out the electron. So you have the photon's energy, you use up some of that energy to kick out the electron, and whatever energy is left goes into the energy of motion of the electron. And so you can see the electron energy is going to be a linear function of the light's frequency, and it will be given by this equation here. And then the reason that the photocurrent is just proportional to the light intensity is also very clear, because every single photon kicks off one electron. So if you double the number of photons, you'll double the number of electrons. So you'll have this direct proportionality between current and light intensity. So this was a very successful model, and as I said, it earned the Nobel Prize in 1922, and at the time it was understood to be direct evidence for photons, period. And in fact, if you open up a lot of textbooks today, physics textbooks, that are talking about this, say a modern physics textbook or a quantum textbook, they will present this experiment as evidence for photons. And yet, over the years, even at the time that Einstein was proposing this interpretation, there was some skepticism about that interpretation and basically looking for an alternative way to explain these results. So going back to the analogy of leaves on a tree getting knocked off by the wind, this model here is talking about the wind as being made of bullets. And, bullets of wind are hitting the leaf and knocking them off one by one. But there were people looking for explanations in which the wind was very much like a fluid, like a wave, that was causing these individual leaves to snap off the tree and kicking out single electrons. And in fact, it wasn't until 1969 that two physicists named Lamb and Scully, in 1969, they came up with an alternative way to talk about this so-called photoelectric effect, where they treated light as a wave, purely as a wave, not as a particle, no photons needed, but they treated the metal atoms as quantum objects. And these metal atoms and the electrons have discrete energy levels. And this is a so-called semi-classical model, because here we're treating light as a wave, not as a photon, but we're treating atoms quantum mechanically. So it's not a fully classical model, it's a semi-classical model. But the key point here is that there's no photon needed to explain the results. The details of Lamb and Scully's argument are a bit beyond the scope of this class, although it involves something called perturbation theory in quantum mechanics, and we do cover that in physics 323, which is our advanced version of quantum mechanics that comes after 302. And in that course, you develop the tools needed to understand perturbation theory and to study how light interacts with atoms and matter. The bottom line, though, from our point of view, is just that as of 1969, we've had a way to understand the photoelectric effect without saying the word photon or invoking a photon at all. And so Einstein seems to have won a Nobel Prize for something that's not quite right. In other words, you do not need to use photons to explain the photoelectric effect data. Now, that's part of the story. The next part of the story is that we're going to show, in fact, that photons do exist, right? So Einstein was not wrong in proposing photons as a model, but the photons are not necessary to explain the photoelectric effect, and Einstein's explanation of the photoelectric effect is by no means direct evidence for the existence of photons. So how then do we know that photons really exist? Well, I'll give you a brief description of an experiment that took one step in that direction, and then we'll dive a little more deeply into an experiment that really sealed the deal and put the nail in the coffin. Okay, so if you're trying to distinguish between waves and particles, one way you can do so is by looking for the existence of the light at one location and not the other. In other words, that would be a kind of particle-like behavior, right? The very term particle kind of implies that an object has a definite location in space. It's either here or there, but it's not both here and there. Whereas a wave can spread out over an extended region. So the experiment that we'll talk about basically asks the question, can light be in two different places at the same time? And if not, then that would be evidence for the particle-like nature of light, okay? So we basically want to take two detectors, put them far apart, illuminate both detectors with the same light source, and see if both detectors ever click at the same time, okay? And if light is a particle, they never should click at the same time. So here's our apparatus. It's very straightforward. We have an incoming beam of light, and then we have what we call a beam splitter, which you can think of as a half-silvered mirror that transmits half of the light and it reflects half of the light. And by that we mean, if you have some intensity of light in the incoming beam, then the intensity after the beam splitter is half in each leg of the beam splitter. And here, at this point, we're not dealing with single photons, right? We don't even know about photons. We're just shining light. It could be a laser beam or a bright light source even, okay? These detectors, we're going to say that they click when they register light. So you get a click when light hits. And it's not an audible click, but there's an electrical pulse that's produced on this wire or on this wire when detector 1 or detector 2 fires. And we basically then want to ask the question, does detector 2 ever fire at the same exact time as detector 1? And to do that, to answer that question, we take the signals from the detectors and we put them into a so-called coincidence counter. And a coincidence counter just counts the number of times that you get a signal from both of these detectors within a short time window, the counting window or the detection window. For this, it's useful to define a so-called anti-coincidence parameter. And we'll give it the uninspired name A. So A is our anti-coincidence parameter, which is given by the ratio of involving three quantities. Okay, we'll start with the denominator first. P1 here is the probability that detector 1 is responding or clicking. P2 is the probability that detector 2 clicks. And PC is the probability of getting a coincidence that detector 1 and detector 2 click at the same time. Right away, we can see that this parameter is going to be a nice measure of anti-coincidence, because if light consists of photons, then that photon will either go to D1 or to D2, but never both at the same time. So either D1 will respond or D2 will respond, but not both. And in that case, the probability of a coincidence will be 0, and A, which is the ratio of that coincidence to the individual probabilities, will also be 0. So if you do this experiment and you find that A equals 0, then that would be evidence for the photon-like behavior of light. Well, let's think about another outcome. What if instead of photons, light behaved in some other way, such that D1 and D2 were firing randomly, independent of each other? Okay, if that was the case, then we can show that the probability of the coincidence would simply be the product of P1 and P2, because if D1 and D2 were randomly clicking and doing so independent of each other, then the probability of the coincidence is given by the product of the probabilities. And if that is true, then this A factor would be the following ratio, but the numerator in this case would equal the denominator. And so the anti-coincidence value would be 1. Now, what if you did this experiment and you found, just empirically, you went out, did the experiment, and you found that A was bigger than 1. I don't know, maybe it's 2. In that case, what you can infer is that the events are correlated. So detector 1 and detector 2 respond in a way that's correlated. Okay, and this could indicate like a clustering behavior or a clustering tendency, where detector 1 and 2 tended to tick at the same time more often than not. So this experiment was done in 1956 by Hanbury, Brown, and Twiss. And I'm not going to get into this too much, but the result was that they found A equals 2. So they wholly expected to find evidence for photons, which would be A equals 0, but they found an anti-coincidence parameter of 2. This work was later repeated once lasers became more available, and they found A equals 1. So once again, not A equals 0. So it turns out that if you want to show evidence for photons, you need to have a source that makes single photons, which is not the same as taking a bright source and attenuating or blocking a lot of the light. You actually want a photon to be generated, one at a time by some photon source. In other words, if you're trying to show that light is composed of photons, you're only going to be able to succeed if your light source has a well-defined number of photons, in particular, one of them. And we now know that the work of Hanbury, Brown, and Twiss in the 50s did not satisfy that criteria. It may surprise you to know, and I certainly was surprised when I first learned, that evidence for photons was not really available until the 70s or 80s. And in particular, there was some seminal work by Clauser in 1974, which was then improved and made much more compelling by Granger, Roger, and Aspect in 1986. So I was 6 years old in 1986, and I had always thought that, once I started studying physics, I had my understanding was that photons had been the existence of photons had been proven and known about in the early 1900s. In fact, they had not been proven to exist until 1980s in my lifetime, which is completely strange to me, but that's where we are. So I'm going to talk a little bit about this experiment by Granger, Roger, and Aspect. And in particular, we'll talk a little bit about how they made a source of single photons and then what the outcome of their measurement was. So here's a very quick overview of how you produce single photons in a way that you can control and make use of for the measurement of the anti-coincidence. So the French group that did this, Granger, Roger, and Aspect, took calcium atoms and excited them with a laser. So they shone laser light on the atom that excited the calcium atom. And when an atom is excited, it eventually will de-excite. And de-excite means the energy that went into exciting the atom now comes out. And the way that this particular calcium atom de-excites is by the emission of 2 photons. And they called this the trigger photon. And the second photon. So the trigger photon has one frequency, F1, and the second photon has another frequency, F2. And if you're wondering why this laser light excites the atom, but then when it decays you get 2 photons out, the reason is the following. We can think of the calcium atom in terms of its energy levels. So we have these 3 lines here representing 3 different energy levels. And the laser excitation takes you from the lowest energy level to the highest energy level here. So that's the laser excitation. And then when that excited atom or that excited electron state de-excites, it does so via a third state, an intermediate state. So in going from the highest energy state to the middle state, you get 1 photon, that's frequency F1, and then going from that intermediate state to the ground state, you get another photon of frequency F2. Now I'm going to move this energy state down here to leave space for a diagram of the actual experiment that they did. Okay, so here we have our calcium atom, which we're thinking of as a single photon source. Well, really it emits 2 photons, one of which we will use as a trigger to tag the release of the second. But the second photon is a single photon. Okay, so out to the left we have this so-called trigger photon. That is sent to a detector. And we'll call that D1 for detector 1. They used a photomultiplier tube, but the exact detector is not so important here. Okay, and we're going to take this signal and send it off over here, and we'll see where that gets used in a minute. The other photon now becomes the photon of interest for our experiment. Okay, and we're going to do exactly the same thing we had originally set out to do, right? We have a beam splitter, and we're going to have 2 other photon detectors. So we have beam splitter, which I'll just label as BS for beam splitter, and we're going to have 2 beams here. We're going to have, I'll call it a reflected beam and a transmitted beam. Okay, so I'll call one of these detectors DT for the transmitted beam, and the other will be DR for the reflected beam. Okay. And once again, we take these signals to our coincidence counter. So these signals are now input to our coincidence counter. But in addition, we have our trigger photon that we'll use as our gate. Okay. So when D1 fires, we're going to make a little electrical pulse, and we only do our coincidence counting when D1 has fired. Okay. So this is called gated coincidence. We have 2 signals, and we only ask the question, are there signals on either or both of these? We only do that when D1 is alive. The key idea here is that we are now only counting events that correspond to the release of this second photon, F2. In other words, if there's any stray light in the room, if there's random instrumental effects from one detector or another, those get completely obliterated and ignored because we only take data when we know that this single photon source is firing out its photon. And lo and behold, when they did this experiment, and they measure the anti-coincidence parameter, they find 0. And remember, 0 means that the light is not simultaneously at both of these detectors. It's either at DR or it's at DT, never both. And so we finally have evidence for photons. As a reminder, this was 1986, which is very recent. So although we throw around the term photon all the time, I think it's worthwhile pointing out just how much effort has to go into actually showing that photons exist. Indeed, the concept of a photon is far more subtle than people had originally thought, including Einstein. Okay, well, we're going to wrap up there, and I hope you are all well, and until next time, take care, my friends.